To me, a scientist is someone who is comfortable with uncertainty and who can adapt to that uncertainty and who can see the grey areas in everything, who can see all perspectives and all sides and then make a reasoned choice.
So hi and welcome to Mug of Science again, a part of Pint of Science in 2021, where we take scientists out of their locked down houses out to the cafe to have a mug of coffee or whatever it might be and find out a little about their science. I'm Tom Carruthers and I've got the pleasure of being able to speak with Dr. Fiona Panther, who is a postdoctoral researcher at the University of Western Australia. She did her PhD at the Australian National University and also did a short stint at the University of New South Wales, Canberra, Adbury type space. That's
Yep.
right, yeah. So, thank you so very much for joining us with Mug of Science.
Thank you for having me.
The first question that we have to ask is to find out what's in your mug today.
So I've got a bit of a Perth specialty. So when I moved over here, I kept hearing stories about the concept of the long macchiato and the short macchiato.
Mm-hmm.
So the long mac, as it's called over here, is a Perth concoction. I'm still not entirely certain what it is. I think it's like a long black with a bit of steamed milk on top. Whatever it is, it tastes pretty good.
Right.
And today I've got a short mac, which is just the espresso with the steamed milk on top. So a
So
bit
like
of
the normal macchiato that you
yeah,
get.
but
right.
it's a short mac as
Short
opposed to
mac,
the
but
Perth
it's
long
as
mac.
opposed to- yeah, right.
Yeah.
I think that's actually what my mum would normally order for a coffee.
Oh, yeah.
But I think on the Gold Coast they might call it a long white, actually. So it's like a long black
yeah.
with a dash of anyway.
Yeah.
Fair enough. So let's find out a little bit more about you as a human before we delve into, because I noticed you've got the Ozgrab jumper on. You're promoting the brand. Before we jump into the astrophysics, find out a little bit about you. When you're not in your academic world mind stuff, what do you do to keep yourself interested? How do you keep yourself entertained during lockdown, for instance?
So yeah, we've been really, really lucky in terms of not being locked down for too long here in Perth. So I mean, I do have a lot of hobbies which are kind of outdoorsy. So this year moved to Perth. Bit of a change in lifestyle compared to Canberra, so I got into surf lifesaving.
Oh yeah.
So over the summer, I've been on the beach down at Floreat every few weeks, sort of checking, make sure everyone's all good, everyone's enjoying themselves, staying safe.
Was that so is that something you started doing when you came here? You had no interest or?
I'd always been interested in it. I just never really had the opportunity, and there's no beaches in Canberra to lifeguard at. So
I'm sure there's a lake there that you could possibly patrol if you wanted to.
Yeah, so it was a bit of something different and something new. Just something that got me down to the beach, got me outside on the weekends. Because during my PhD, I kind of lost track of a lot of my hobbies. So I've done a lot of quite active stuff to get back into it: social sport, playing volleyball, playing netball, getting into adult gymnastics, things like that. Sort of to really get out and do something physical rather than just sit all the time.
Because there would be a lot of sitting in the kind of work you do, because the stuff that you're playing with is astrophysics, especially with Ozgrab. When as soon as we start talking Ozgrab, we're talking about gravitational waves, which of course were only they were predicted over 100 years ago by Einstein, but they were first detected properly only a couple of years ago.
Yeah.
Did you have any involvement in that yet, or was that prior to you shifting over to
So
space?
that was a big, actually, motivator to shift over, because I was sort of very much on the periphery. I was in the astronomy community in 2015. It was, I think, the first year of my PhD. So I was involved in astronomy, but not the detection. And so I remember my first experience of this was I was at a conference in 2016, 11th of February, around 3 a.m. We all sat down and we watched this amazing press release from LIGO where they said, we've detected gravitational waves. And I kind of was thinking then, like, oh my God, how cool would it be to be part of that? 2017 rolls around, first neutron star merger. I had friends who observed that in the days after it happened, but I was just so much on the periphery, I wasn't involved. And so when I saw the job come up here in Western Australia to actually work on the detection pipeline, so actually doing the detections themselves, I just jumped at it and thought, this is perfect. It's a bit different from what I used to do, but I feel like I've got the skills, and to be involved in it now is just incredible.
So I do want to go a little bit more into the detection of gravitational waves, because I'm super excited about this. But let's go back into what you used to do a little
Yeah,
bit, so
sure.
we find out a bit more about your PhD. What were you actually studying in your PhD?
So my PhD thesis, the title is The Origin of Antimatter in the Milky Way.
Just a small
Just
problem
a-
you want to try and solve for a
Just
small PhD?
a little problem. It's only been around for 50 years, and that's only because we found out about it 50 years ago. So gamma ray telescopes were first launched into the atmosphere, first on balloons and then into space, about 50 years ago.
Right.
And when they did that, they put their telescope up and they were expecting to see this nice flat spectrum that you would predict from energetic particles scattering off one another. And what they actually saw was this really interesting little bump in the gamma ray spectrum at 511 keV. And where that's coming from is electrons and positrons annihilating with each other. So they interact and then they obliterate each other in this puff of gamma rays, and you get exactly 511 kilo electron volts of energy out. And so this line was not predicted, it wasn't expected, and everyone kind of went, oh, I wonder where that's coming from. And it's been a really persistent mystery, and more observations over the years have actually managed to build up a picture of where this annihilation is coming from, which means we know where the positrons are annihilating. We're still not sure where they're coming from, and my PhD was trying to understand, are they coming from certain types of dying star? So these stars explode, they leave behind radioactive material which radioactively decays to make positrons, which
Right,
then
so-
annihilate.
Okay, so we know we found this weird signal out of the middle of nowhere. We now know the origin of where the signal is, and that's where this stuff is breaking down, but we don't know where the stuff comes from that was first made to be able to do the breaking down thing.
Exactly, and it's really hard to account for it because there are so many things in the universe that produce positrons, but the whole census of it doesn't quite add up. There's actually way more positrons annihilating than we expect. They're annihilating in weird places as well. So they're usually located, the radiation's coming from where old stars are. And positrons are something you actually expect to come from young stars. And so the distribution of the annihilation is very different to what we would predict.
Right.
And that makes it a really tricky problem because there's maybe a source there we haven't actually accounted for in the modelling.
And this, I think, is actually one of the areas of science that I get super excited about, right? Is when you have, it shows that you're at a point of actual discovery of something new. Yeah, when the models perfectly match exactly what you're predicting, that's great. It shows that we have a complete understanding. At least the model kind of like matches that particular subset or that particular situation well enough. But these situations where all of a sudden you have unaccounted matter turning up in places or signals turning up where they're not supposed to or whatever, that can be really, really exciting.
Yeah.
Did you find that excitement as being the thing that drove you into thinking about going into a PhD? Or
Yeah, I think I was just very curious about unknowns, but unknowns where we knew there had to be an answer. Because I think it was probably around my third or fourth year I had this conversation with a professor at Auckland where I did my undergrad, and he was kind of saying, if something exists and we observe it, there has to be an explanation. You can't just have something known, like we see something, we can't not have an explanation for that, there has to be one. And that was what really drove me into studying this particular mystery, was the idea that there has to be some explanation, and it's just a matter of picking apart all of the information to try and actually find it. And it was that curiosity that drove me into doing this particular PhD, actually.
So you did your undergrad in New Zealand?
Yeah.
Are you originally from New Zealand, or did you go there for your undergrad, or?
So it's a bit of a long story. So I grew up in the northeast of England. I was born in a small town called Ashington.
Yep.
We moved to New Zealand when I was 15. So my parents moved for work, and I obviously moved with them. And then I lived in New Zealand for about 10 years, did my undergrad in Auckland, and then, because we lived in smaller towns, we lived in Matamata first, and then a town called Tauranga, which is on the coast, really beautiful place. Then I moved up to Auckland, spent about 5 or so years there, and then got the opportunity to do my PhD in Australia and hopped over to Canberra. Came to Perth then, I think about, just over a year ago now.
Were you always passionate about science? Was there something in particular that triggered that interest to go, you know what, I want to do an undergrad in astrophysics, or?
I've always been really interested in science. So my parents were sort of first in their immediate family to go to uni, and then they really encouraged my interest in science. They went to uni to study dentistry. So they always really encouraged that curiosity I had with all the why questions. Why is the sky blue? Why is this like this? Why is this? They really encouraged me to find the answers for myself though. Sort of if they didn't know, they'd show me how to find the answer. And so I really grew up with science just being a part of my life. And I was super passionate about it in school, and I was really fortunate to have really good science teachers who saw it and kind of nurtured that passion all the way through. I think I really got interested in astronomy, I forget, it must have been 97, 98. We saw the Hale-Bopp comet actually from our back garden in Britain. And I remember looking at this comet and thinking, that's so cool. And that really twigged that, whoa, there's all of this universe out there, kind of passionate about space for me. And so from there, I kind of went through always thinking, this is really, really cool. I just don't know that I can do it. And then when I was in year 9, so I was 13, so like Australian year 8, slightly different system in the UK, I had this teacher he had done a PhD. So Dr. Fox, he'd worked for NASA, and he basically said to me, look, this is a thing that you can do. This is what a PhD is. You could go on and be an astrophysicist if that's what you want to do. And that was my first sort of, there's this thing called a PhD and you get to go and research. And from that point on, I was set. I was just, no, I'm going to get a PhD. I'm going to do that. And that's what I wanted to do sort of from there.
So a big call out to Dr. Fox for helping get this astrophysicist here into Australia. I trust that you are watching this Pint of Science in Australia. We'll make sure we get a copy out to him, right? So always passionately interested about like that kind of discovery science aspect.
Yeah.
Was it specifically astrophysics that you did your undergrad in, or was it just a more broader?
I did my undergrad actually in physics and maths, and so I struggled horribly with maths in school from quite a young age. So
was that really a barrier to trying to get over? Or?
It was it was in a psychological sense. It was because I'd struggled very much with the mental arithmetic, and so I had this like fear of mathematics. And it wasn't until I got into my last year of high school where I had a teacher who was very understanding and really encouraging and saying, look, you don't have to be able to do it in your head. You can just write it out. You can do it on the paper. You're actually quite good at this, and what you just need to work on is just practicing the kinds of problems. And so I ended up getting relatively good grades in my final year, and I went on to major in maths and physics. And so because of his input, it wasn't too much of a barrier, whereas I think if I hadn't had that, it would have been more of a barrier to me. And obviously it's helpful to use a mental arithmetic sometimes, but it's not necessary. Like I don't need to know my times tables to do what I do, because I do most of what I do on the computer. So yeah, it wasn't too much of a barrier, although math is extremely important to physics in ways that actually I didn't even realize. So I learned going through like, all of this mathematical stuff that describes how surfaces curve and bend, that's actually vital for the kind of physics that I'm interested in, which is gravitational waves.
Of course. So thank you, you've just done my segue for me. Let's talk about gravitational waves. I've been speaking to a couple of people over the last couple of months in various roles as well as for this. My understanding, and please, this is where you completely correct me because I'll be utterly wrong, I'm guessing, is that gravitational waves are, if you imagine the entire universe as being effectively a single two-dimensional surface, but then the three-dimensional part of that surface is it starts to get, when there's things that are heavy, you've got large mass, they're sitting on top of that surface, they kind of pull down, but then there's these kind of ripples, a little bit like the ripples of a pond, that go across that fabric, and we might be able to observe them. Is that roughly?
Yeah. So you can certainly reduce it to say we only have two dimensions of space. So we've got sort of two different axes, and then you've got your flat sheet of space-time. That's assuming there's no third dimension. And then so gravity is what we perceive as any curvature. So the curvature is what we feel as gravity.
Right.
And then we can have ripples in that sheet. Now what actually is happening is you've got to imagine it almost as like a 3D mesh.
Right.
And so what's actually happening is if you've got a mass, then in all three dimensions are curving towards that mass. So it's the third dimension
really
isn't very hard to draw, which is why we simplify it. So the third dimension isn't actually the bending. The third dimension is actually another part of that lattice.
Right.
And then the ripples are what we perceive as the changing
Mm-hmm.
in the joined together points that we imagine in that lattice.
Kind of like pull and squeeze into each other.
Yeah.
Now I'm wondering if we can make some cool 3D animation to try and demonstrate that, because I think, thank you for actually explaining that to me.
Yeah.
That at least that's the picture that we always see.
Mm-hmm.
It's that surface that's
Yeah.
wobbling along. Right, but these waves, they're tiny.
Yeah.
How tiny?
So the thing with space-time is that fabric. It's extremely stiff. It's very, very hard to make it bend. That's one of the reasons why gravity is actually such a weak force. Mm-hmm. So things like the forces that hold together atomic nuclei and even the electromagnetic force are orders of magnitude stronger than gravity. Mm-hmm. So it takes a lot to make it ripple and bend. And so when we're detecting gravitational waves with interferometers like LIGO and Virgo, and in the future CAGRA, which is the Japanese detector, we're detecting changes in distance which are on the order of the fraction of the size of the proton. So you're detecting something which is on the order of less than an atomic nucleus. That's how stiff, and those are coming from massive cataclysmic events. We're talking tens of solar masses of black hole merging together to create this huge events that emit as much energy as put out by the sun in its entire lifetime. And that's what it takes to actually perturb space-time just that little bit. Of course, these events are very, very far away as well. So if there was one next door, things would maybe be a bit different,
bigger, yeah.
But it's still extremely stiff.
Wow. So I've heard the analogy in the past of, like, smaller than a human hair. Of course, yes, that's true, but it is so much further than just smaller than a human hair.
Yeah.
I had absolutely zero concept of being able to how to scale what that looks like, because even an atom is like a normal a normal atom is like, if a proton was like the head of a pin, the first electron that would be out there would be about a football field away, right?
Yeah,
So, and we're talking about less than the width of a proton.
So maybe this is a better way to describe it. So when we're detecting gravitational waves, we're detecting very, very accurately changes in distance. Mm-hmm. And it's a little bit like if you imagine having a human hair on the moon, us being able to measure the diameter of the human hair from here on Earth. That's the kind of resolution that you've got to have. It's incredible. It's very, very difficult to imagine.
Right, so the technology here is huge, and I know there's been a lot of work that's happened in Australia to make these detectors even just possible.
Yeah.
I believe it was the Prime Minister's Prize for Science last year. I think it was last year.
Last year, 2020.
That went to 4 Australians in the Osgrav space around this. I mean, my mind is still blown how you could even detect something like that. You said LIGO and Virgo. Let's just very quickly talk. What are they? I know that they're detectors of some type. Can you give a bit of a description of what they are?
Yeah, so they're a type of what we call interferometer. An interferometer is something where we use light usually to detect changes in length. So what you've got with LIGO and Virgo, the LIGO detectors, there's one in Washington in the US, and there is one in Louisiana, Livingston and Hanford. And what they are, Virgo is the same, it's in Italy, but you have an L-shaped detector. So each of the arms of the L are 4 kilometers long. And
like 4Ks.
4Ks, yes. that is 4 kilometers, and that is 4 kilometers.
Right.
And so, So what you've got is down each of those arms you send a laser beam. It reflects off a mirror. It comes back, and those beams get combined together. And when you combine those beams together, you get an interference pattern, patterns of light and dark fringes, and that's what we detect, those light and dark fringes.
Because here's me going unquantumized. That's the wave part of the light.
Yes,
and so because you get that kind of constructive and destructive interference between where the lasers overlap, right?
Yes, exactly.
Okay.
And so what happens is if a gravitational wave passes through, the arms of the interferometers ever so slightly change length. And when those arms change length, the interference pattern is going to shift, because what the interference pattern looks like depends on how long the arms are. And so if you can detect the movement of the arms, and the gravitational waves will make them move in a very specific way, then we can detect the gravitational waves by looking at the light and dark pattern that's coming out. And so we do this in 3 different places at the moment, and what we can do then is we calculate the delay in the time of the gravitational wave arriving at one detector, the next, and then the next. And from that, you can triangulate where on the sky it's come from.
That way.
Yeah.
And you can point the other telescopes there and you can then
Exactly,
see what
yeah.
happens.
Yeah.
How much notice do you get? Like, do you get like 2 days notice or 20 seconds or?
This is actually a really exciting question because this is something which has changed, and it's something that me and my group is actually actively working on.
Right.
So during the first couple of observing runs, there was quite a big delay between the data being obtained, so seeing the actual data, which is the interference pattern. It then gets processed through several different steps.
There would have to be quite a bit of computation to figure out what you're looking
Yeah,
at, right?
there's a
Because there'd be
huge
just so much thermal noise that would be just going on all the time, right? So you have to get rid of all of that.
We do, and so there's a lot of cleaning goes on. We have to remove certain glitches, and a lot of that is done before the data actually gets to us.
Right.
But when we get it as the pipeline teams, there's still quite a lot of processing we have to do. And so we basically sift through the data and we listen out essentially for the signals that are coming in. And there was quite a long delay in the first couple of observing runs, on the order of maybe hours or even days for some of the signals, because you have to be sure of what you're looking at. During the third observing run, things started changing a bit because we started putting out public alerts, which meant that the astronomy community and even the general public could access these. They were being notified within a few minutes of these mergers happening, anywhere from about 10 to 30 minutes.
And there was a little bit of a risk of like, this might not be, we're not 100% sure, but we think it might be a thing. Right.
So we sometimes had some retractions. Now the problem with that is if you're looking with an optical telescope, whatever's happened, especially if it's a neutron star merger, you're not going to start seeing light come out, optical light, that you can see with a regular optical telescope for maybe hours to days. So it's not too much of a hassle if it takes us a while to process that.
Right.
The thing is, with neutron star mergers, when the things actually merge together, you get a burst of gamma rays within milliseconds of that merger. And so what you want to do is you actually want to say, we see a neutron star mergers coming because we see this in spiral waveform coming early, and then the telescopes can be ready for it. And so there's recently been an experiment, there's a paper just being published about this, where our pipeline and another search pipeline called GST-LAO, what we actually did was search for these truncated waveforms. So we're looking for neutron stars where we can detect them 70, 60, 40, 50 seconds before merger, send out the alert within a few seconds of that, and then alert all of the observatories. And what we found is that you actually can detect an event like 170817, this very famous multi-messenger neutron star merger, about a minute before the neutron stars merge, which gives telescopes a lot of time to start looking. Yeah.
That is so cool. So it means you get all this valuable information about stuff before it happens, because there is just so much sky to be looking at, right? And so being able to focus in on where the interesting stuff is happening.
Yeah.
What a fantastic tool that's become. The specific part that you're working on in this pipeline, is that specifically the processing or improving those steps, or what is it that you're doing when you go and sit in front of a computer?
So at the moment, so our pipeline's called SPIR, so SPIIR. It's basically we name it after the way we filter through the data. And so what I'm actually working on at the moment is working on improvements to the pipeline to enable it to run faster and to also include data from more detectors.
Right.
So originally LIGO started up with just the 2 detectors in the US, Hanford and Livingston. Now we also have to incorporate Virgo data, and it's really tricky to actually do this from the pipeline's perspective because the noise in each of the different detectors is quite different.
Right.
Which means the glitch rate is different, and because sometimes our pipeline, all of the pipelines, we get a bit confused between these transient glitches which can come from everything from earthquakes to air conditioning units with parts that are flapping around on them.
Right.
You know, you have to be able to distinguish between those and real signals. And if you've got quite a lot of noise anyway, like is the case with some of the newer detectors, it's quite challenging. And so at the moment we're working on making sure that we can use data from all of the detectors, including CAGRA, which will come online in 2022 as well.
Where's CAGRA?
CAGRA's in Japan. So this is the Japanese detector. That will also join. So we need to be able to use the data from all the detectors. So that's one thing I'm working on. And previously we've also vetoed all detections where there was just one detector that detected the gravitational
but
wave.
The others don't, because it's Is there
They
a
may
chance
be.
that it's just like such a small signal that the other one was a little bit better positioned with, or something?
In some cases, yes, but usually it's because the detectors don't have 100% uptime. So sometimes you've genuinely only got either Hanford or Livingston running because they may be doing a bit of an upgrade, maybe they're cleaning something. And so we have to account for that 30% of the time where you've got only one detector. In 03, Spear couldn't detect during those times, so one thing that I'm specifically working on is actually to make sure we can do those single detector events. We're also looking back at 03 data, so the past observing run, which is from 2019 to 2020, we're actually going to be processing that offline and checking and making sure that we detect all of the events that we think we did, and maybe there are some that we missed in there online as well.
Which might improve your algorithms to be able to do that fast turnaround.
Yeah.
Is there any, do you know if there's a pipeline, or sorry, not pipeline, plans? Do you know if there's any plans for there to be a potential interferometer built in the middle of Australia somewhere?
So yeah, this is a really exciting possibility. There's a lot of different plans, a lot of different future detectors planned. One of the OzGrav projects is called NEMO, which is the Neutron Star Extreme Matter Observatory. And so this is a detector that would be placed somewhere in Australia. They're currently doing site studies for this. And what it would do is it would be looking at actually the moments after the merger of neutron stars. Because in those moments after merger, the neutron star is still kind of ringing, it's still vibrating.
Right.
And if you've got a detector that can detect frequencies which are on the order of kilohertz, at the moment LIGO operates between about, we're sensitive between about 30 and a few hundred hertz, about 500 hertz.
Right.
However, NEMO would look at kilohertz frequencies from these neutron stars which are rapidly vibrating, and it tells you a lot about what the neutron star looks like inside. We don't know what's inside a neutron star. We know it's neutrons, but we don't know what sort of state of matter. And that's one of the big questions, is this equation of state, which you can probe with a detector like NEMO, which would be proposed to be built here in Australia.
Well, that'd be cool if we got it here somewhere. I think we have kind of already touched on this, but I think this will be almost my last question about the impact that your work is having. So one of the huge enabling factors I think that I'm seeing out of gravitational waves, even though we don't necessarily have a direct impact on my mum or my grandparents or someone like that, but being able to be this wonderful tool to be able to say, hey, there's a bit of interest over there. Are there any other positive impacts or any other benefits that we can take out of gravitational wave detection?
I think a lot of it is that kind of, in terms of the pure science, is that curiosity. We're looking at the universe in a way which we really never imagined that we could. We're seeing something other than light. We have another way, it's another sense, I guess, to add to the astronomy arsenal. In terms of impacts kind of closer to home, certainly my work, we're actually using frameworks for the software which are used in industry. So we're actually using video streaming, audio streaming software as the framework to get the data through the pipeline. It's called GStreamer. In terms of OzGrav in general though, there are several research translation projects which are taking place. Everything from like early warning of earthquakes to LiDAR for autonomous cars.
Could you plug an earthquake detector into the back of LIGO and get all the noise and just be able to...
That's actually something,
big
it is something that people have actually looked at doing, because obviously the detector is quite sensitive to seismic noise.
Yeah.
And we have to suppress the seismic noise, and it turns out that a lot of those technologies can actually be used to warn of earthquakes ahead of time, because you get those P waves which arrive first.
Before
the big one, yeah.
That's kind of cool. I had no idea about that one. All right, so we will be wrapping up this one now. There is one last thing that I must ask, and we've been asking everyone who we get on board with Mug of Science. I'd like you to finish this sentence. To me, a scientist is someone who... ...
It's a good sentence. To me, a scientist is someone who is comfortable with uncertainty and who can adapt to that uncertainty and who can see the grey areas in everything, who can see all perspectives and all sides and then make a reasoned choice. That's what being a scientist is to me. That's what my training, I think, has given me. And that's one of the things that I think it's helped me with in my life, is that I feel comfortable dealing with some of the uncertainties I've faced over the course of my nearly 30 years on Earth. I've dealt with a lot of uncertainty at times, and being a scientist, it's just getting comfortable with that. It's okay to not be sure. It's okay to have a bit of a guess and to just try something out. And if it doesn't work, hey, just go try something different. The next thing you try might be the brilliant idea that wins you the Nobel Prize.
Well, best of luck with that Nobel Prize coming to you. That's all we have time for on this little episode of Mug of Science. Thanks for joining us this morning, if that's when you're watching. Thank you again, Fiona, for taking the time to catch up with me and have a chat. And this has been part of Pint of Science Australia. I'm Tom Carruthers. Thanks again.